Good morning, ladies and gentlemen. We're going to do 4.5 today. We're going to be talking about integration by substitution. So our objectives are that we're going to use U substitution to manage integrals that are not easily integrated. It's nice if you put a period. Remember that there is no product or chain rule for integration. So we're going to do something that is very similar, but there really isn't a chain rule. But instead, I'm going to do my U substitution. All right, so let's go back and remember the way it's officially called. So if I have an integral, and it is a composition of f of g of x times the derivative g prime of x dx, and it really does look like the chain rule because I have a composition and then I'm taking the derivative of the inside, well then this turns out to be f of g of x plus c. So here's what we're going to do. This is what I'm going to call the inside. So I'm going to let u equal g of x, and then I take the derivative of u, and I'm going to get g prime of x dx. And then this would be substituted up here, right? So then I can have a u and a du. So it simplifies my integral. So let's just do an example and start that way because I think that's the easiest way to talk about U substitution. So I'm going to have the integral of x squared plus 1 quantity squared times 2x dx. All right, so this is what I would consider the inside. So I'm going to let u equals x squared plus 1. So then du is going to equal 2x dx. So notice that 2x dx is the same as here. So then I can rewrite this integral as u squared du. Well, that looks really simple. So when I integrate that, I'm going to get u to the third over 3 plus c. I need to substitute u back in. So my integral is going to equal x squared plus 1 to the third divided by 3 plus c. And then I would write what my integral was. And I'm going to be a little bit lazy for right now. Okay? So that's actually a very straightforward U substitution. So let's do another one where it's a little bit different. Okay, so in my next example, I'm going to do the integral of x times x squared plus 1 quantity squared dx. If you wanted to, you could rearrange it and do x squared plus 1 quantity squared x dx. So I'm going to start again on the inside. So u is going to equal x squared plus 1. du is 2x dx. So if I look over here, I have the x dx, but I'm missing the 2. So I need to introduce a 2 on the inside, which means I need to introduce a 1/2 on the outside. So I'm going to rewrite it like this just to show you one time. I usually don't do this when I'm doing U substitution, but just to illustrate the point, now you can see what it looks like. So now I have, here's my inside u, here's my 2x dx du, so then my integral becomes 1/2 times the integral of u squared du. Okay, so that's pretty easy. So then if I do that, here's the half, and then I'm going to get u to the third over 3 plus c. Remember, it's an indefinite integral, so I always have to add my constant. If I clean that math up, I get 1 over 6 times u cubed plus c. Substitute back in, and I get 1 over 6 times x squared plus 1 quantity cubed plus c. And then my integral of x times x squared plus 1 squared dx would equal that math that you can't see. All right, so another thing to remember is that if I want to check my work, I could take the derivative of this, and I would get back to where I originally started. So remember that an antiderivative and a derivative are opposites of each other. So I'm just going to do this once just to show you that it works. So I'm going to take the derivative of my solution of the 1 over 6 times x squared plus 1 to the third plus c. Alrighty, and I guess technically this guy should be in here. So here's the 1/6, and then I have a 3, and then I have x squared plus 1, and then to the second, right, times the derivative of the inside, 2x. The derivative of a constant is 0. So 3 goes into 6 2 times. That 2 goes away. And notice that I get x squared plus 1, quantity squared times x. So I got my original function. So the derivative verified that I got the correct solution to my integral. Alrighty. So U substitution does get to be a little bit more entertaining, but let's do another couple of examples. Move my Starbucks coupons. Okay, for our next one, it's going to look like this. I'm going to have the integral x times the square root of 2x minus 1 dx. You ready? So remember, I want to start on the inside, so I'm going to let u equals 2x minus 1. We got a lot of these guys in these examples, sorry. So my du is 2 dx. And again, notice I'm missing the 2, so I'm going to introduce a half on the outside. And I don't often show that step, but you can if you need to. So again, if you need to show it, it would be 1/2 that I'm introducing on the outside. Here's the 2x minus 1, and then I have a 2x dx on the inside. If I rewrite this, this is 1/2 times the integral of u to the 1/2 du. If I integrate, here's the half, and then I have u 1/2 plus 2/2 is 3/2 divided by 3/2 plus c. So I get 1/2 times 2/3 u to the 3/2 plus c. 2's cancel. So I get 1/3 u to the, where's all my work? I'm just looking at all of my work, and u to the 1/2 plus 1, 2 over 2. I wonder if I did something wrong. I have no idea what I did when I was doing that math. Whew, that's tricky. To the 3/2 plus c. Did I do a mistake? So let's see. I introduced a half on the outside. I have u to the 1/2, and then I have plus 1 plus 2 over 2, 3/2 divided by 3/2. I have no idea what I did because this looks way easier than what I did in the video. Oh, I know what I did wrong. My bad. Sad day. I forgot that guy because I don't have that variable. Whoops. So we're going to go back and redo, and this is like the third time through this video, so I'm not going to start again because I seem to be having brain farts. I need to solve for x, and I'm going to do it from there. So I'm going to get 2x equals u plus 1. Whew. So x is going to equal u plus 1 over 2. And you guys are probably saying, come on, Bang, get it together. All right, so I managed introducing the 2's, but now I have to introduce that x. So if I go back to the beginning, here we go again. So I have the square root of 2x minus 1, and then I have a 2x dx. So now if I do my u substitution, I'm going to have a 1/2 on the outside integral. So I'm going to have u to the 1/2, which is my 2x minus 1. There's the 2x, okay? So I'm going to have my 2 that I introduced on the inside. I'm going to have my x, which is u plus 1 over 2, and then I have my dx. Well, on the inside, these 2's cancel, right? So I end up with 1/2 times the integral of u to the 1/2 times u plus 1 dx. The easiest way at this point to manage this one is, and I'm just looking to make sure I didn't make any more stupid mistakes, is to distribute these two guys. So I'm going to have 1/2, and then I have u to the 1/2 times u to the 2 over 2 is u to the 3/2 plus u to the 1/2, and then du, bad variable, du, bad variable, du, okay, and put my parentheses so my grader would be happy. So then I'm just going to manage all my math. So here's the half. U to the 3/2 plus 2/2 is going to be u to the 5/2 divided by 5/2 plus U to the 1/2 plus 2/2 is 3/2 divided by 3/2 and then plus C. Okay, so I'm going to clean up all that math. So I have 1/2 times 2 over 5 times U to the 5/2 plus 1/2 times 2/3 U to the 3/2 plus C. Alrighty. Twos cancel, so I get 1/5 U to the 5/2 and I get 1/3 U to the 3/2 plus C. Alrighty. So if I look at this, right, I'm going to multiply this guy by 3 over 3, and I'm going to multiply this guy by 5 over 5. So I can add all of this together. So I'm going to get 3 plus 5 is 8 over 15. U to the 5 plus 3 is 8. 8/2 plus C. So this is 8 over 15. U to the 4th plus C. Now I need to finish and substitute back in. So my original integral, which was way the heck back up there, so the integral of x times 2x minus 1 dx is going to equal 8 over 15. And then I have my u. Where was my u? 2x minus 1 to the 4th plus c. Now we're done. Sad day. So that's a nice way to finish that problem, since it only took me 2 tries. All right, in our next example, so sorry that made your video just a little bit longer, I have the integral of sine squared of 3x times the cosine of 3x dx. Yay trig. So remember, again, I want to start on the inside, so I'm going to let my inside kind of be this, because remember, sine squared x is the same thing as the sine of 3x quantity squared, so this is what I'm going to consider as my inside. So I'm going to let u equal the sine of 3x. So du is going to be the cosine of 3x chain rule times 3 dx. If I rewrite that, du is 3 cosine of 3x dx. So if you'll notice, I'm missing the 3. So if I rewrite my integral, I'm going to put a third on the outside. Sine squared, or sine is my u, so u squared du. Okay, and I chose not to rewrite it with the 3 on the inside because I think you probably understand at this point. So if I integrate this, I'm going to get 1/3 u to the 3 over 3 plus c. So I get 1/9 times u to the 3rd plus c. This is 1/9. My u was the sine of 3x, but it's cubed, so I'm going to stick my little cubed guy right there, plus c. And then if I report my answers well, my integral of sine squared 3x cosine of 3x, the x has to go down there, and then I'm done. So that was actually fairly straightforward. The next application that we're going to do is definite integrals with our U substitution. And I just really want to do one problem because remember, with definite integrals, it does create kind of a unique situation. So when you do a definite integral with U substitution, so if I have f of g of x times g prime of x dx, and remember, I'm going to let u equal gx, so my du is g prime of x dx. Then I have to manage my indexes or indices, and I actually don't know how to spell that word, so I'm just not even going to write it. I have 2 choices. One would be, once I'm finished, to substitute u back in and use the original indices. The other one would be to evaluate u and do, whatever I let u be. So I'm going to evaluate u of A and u of B and create new, I have to write that word, INDE, indices. I have no idea. So I'm just going to write indexes, even though it's really bad grammar. I'm so sorry, but I can't figure out how to spell indices. All right? So My preference is usually to do the first method where I use the original indices, but sometimes in a multiple choice version, you do have to change the indices, and it really doesn't matter. You'll get the same answer both ways. So let's do an example so we can talk about this. So for our example, I'm going to do the integral from 0 to 1 of x times, and boy, we've been doing this one a lot today, to the third dx. So I'm going to start on the inside. U is equal to x squared plus 1. Du is 2x dx. I need to introduce the 2 because I'm paying attention that I actually have the x. So when I rewrite it, I'm going to have 1 half integral 0 to 1. I have the 2, so I'm going to have u cubed du. So if I integrate it, I'm going to get 1 half, and then I'm going to have u to the fourth over 4 evaluated from 0 to 1 plus c. Alrighty? The second method would be evaluating u. So if I do u of 0, I'm going to get 1. And if I do u of 1, I'm going to get 1 plus 1 is 2. The second method, so sorry, let me finish the first method. So here's the half. I substitute back in my u, so I have x squared plus 1 raised to the fourth over 4, and I would evaluate from 0 to 1 plus c. That's the first method, so we'll label that guy number 1. The second method would be to change my integrand limits and do it from u. So when I had 1 half u to the fourth over 4, I would integrate from 1 to 2 plus c, righty? Okay? And then I would evaluate, I guess you can't see all of it, from here. So then I'm just going to show you this one. Here would be the 1 half, and then I would have 2 to the fourth over 4 minus 1 to the fourth over 4 plus c, and then I would finish that math. But notice when I get to here, I'm evaluating the original function. So it really doesn't matter which method you choose. My personal preference is the first method, so this is what I like to do. I only do this if when I'm doing the problem, I notice that my integrand limits have been changed. And if they've been changed, then I know that what they did is they reevaluated my indices by evaluating the original indices in what I allowed u to be. Alrighty, so that's just kind of a personal preference, or if you're paying attention to the answers that you're given. One last little topic to talk about, and that's talking about integrating even and odd functions, because sometimes this can save you some work. So remember that an even function is going to be symmetric about the y-axis, right? And if you'll remember the test for symmetry and I get the original function, then I would know that the function is symmetric about the y-axis. And so let's talk about what would happen if I integrate an even function. So let's say I'm going to go from a negative a to a, and yes, I have a crappy picture, but area 1 and area 2 are equal, right? Well, if I chose to integrate to find the area under the curve from a negative a to a of f of x dx, because each of these sides are equal, then I could also do 2 times the integral from 0 to a of f of x dx. But that only works when I have mirror images or something that is symmetric about the y-axis. Okay? The other one would be if I integrate an odd function. Remember, odd functions have symmetry, or they're symmetric about the origin. The test for symmetry, if you'll remember, is that all of the signs are the exact opposite. And let's say I have maybe a cubic function that looks like this, and I'm going to integrate from a negative a to a, and I have a negative area and a positive area, and yes, those two areas are equal. You have to trust me. So if I wanted to integrate from a negative a to a, and I did f of x dx, I would actually get 0 because since these areas are equal, and this area is negative, and this area is positive, the two areas would negate themselves, and then I would have 0. Alrighty? Alright, I lied. One more last topic, and then we're really done. And it's just a simple problem. It's an application of what we've been doing. So this example is going to say solve the differential equation Alrighty, so let's say we're given dy dx is equal to 10x squared over the square root of x cubed plus 1. So to solve the differential equation, I'm going to cross multiply. So I'm going to get that dy is equal to 10x squared over x cubed plus 1 dx. Well, if I'm solving the differential equation, that means I want to go back to, I want to solve for y, okay? So to be able to solve for y, I'm going to integrate this side, and I'm going to integrate this side. And remember that when you're showing your work, they want to see that you've cross-multiplied, and they want to see that you set up the integral. Well, the integral of dy is y, so I'm going to get y equals, and then I'm going to have the integral of 10x squared dx. Oops, I'm going to scoot this guy up here. I'm just going to put him over here. And I have x cubed plus 1 to the negative 1/2. So yes, it's a little crappy looking, but you'll get over it. So I'm going to do my U substitution. So U is going to equal x to the third plus 1. Du is going to be equal to 3x squared dx. Well, I can move this 10 outside before I start, and then I'll write it and make it look prettier. So I have x cubed plus 1 to the negative 1/2. I'm going to put the 10 outside, x squared dx. Well, now notice that I'm missing the 3, so I'm going to introduce a 1/3 on the outside, and then I have u to the negative 1/2 du, which is pretty easy, right? If I integrate that, I'm going to get 10 over 3 u to the positive 1/2 divided by 1/2 plus c. So then I flip the 2, so this is 20 over 3 u to the 1/2 plus c. And I'm running out of room, so I'll go to the next page. Okay, so I had that y is equal to 20 over 3, and then I had u. Well, my u was x cubed plus 1 to the 1/2 plus c, and then we're done, which is actually really nice. All right, now that is truthfully it for the day. I will see you tomorrow.